To start this lesson off, we're going to go over a few important points about graphs, just a little bit of review. Most graphs are two number lines, and they show the relationship between two separate quantities. So for example, on a position versus time graph, the slope of a position versus time graph is our velocity. And on a velocity versus time graph, the slope is acceleration. Also important to note that on a velocity versus time graph, the area under the curve is the displacement. So how can we describe the motion of the golf ball? How can we describe the motion of the golf ball? So let's start by describing the motion of the golf ball as it falls. At the very beginning, how fast is it going? It's not moving at all. So that means our velocity in the beginning is 0. Now as I drop it, what's happening to the speed? What is happening to the speed as I drop it? Well, it's starting from rest at 0, and then as I drop it, it speeds up. Our velocity is increasing. Let's go ahead to this next slide. So what can we know? Well, we know that as we drop the golf ball, it's speeding up on the way down. And we also know that the velocity at the top is 0. What about the velocity final at the very end, at the bottom? You guys might think it's 0 because it hits the ground and it stops, right? But I don't want to know the velocity right as it hits the ground. I actually want to know the velocity right before it hits the ground, right here. We don't know that right now. All that we know is the initial velocity is 0, and we know that it speeds up as it goes down. What can we measure? What can we measure? Well, we can measure time with a stopwatch as soon as it leaves my hand and hits the floor. We could also measure the distance from the floor to the golf ball. So the next question I have for you guys is, given those things, the things that we know and the things that we can measure, what can we then calculate? All right, so what can we calculate? Well, we know that we have distance. We can measure distance. We know that we can measure time with our stopwatch, and we know that our initial velocity is going to be 0. What if I wanted to find the final velocity? Well, I just have to select the equation that has the 4 variables that I want. So I want these first 4 variables, so the only equation that has all 4 of those variables is this first one. What I want you to do is pause the video and solve this for final velocity. All right, now that you've paused the video and done that, I'm going to go ahead and show you how I would solve for it. So I would first, because I've got 1/2 on this side, I would multiply by 2 to get rid of it on this side. Whatever I do on this side, I have to do on this side. So if I multiply by 2 to cancel these, then I also multiply by 2 here. The next thing I'm going to do is I am going to subtract this initial velocity. So I'm going to subtract velocity initial, subtract velocity initial. Now the last thing I'm going to do is I'm going to divide by time. Divide by time. So I'm going to go ahead and write the equation up here. What I get is that velocity final equals 2d minus velocity initial divided by time. That is my equation that I would use to solve for final velocity. So now, what if I said, what if I wanted to calculate the acceleration? So now this time around, I still have the distance, I can measure the distance. I still have the time, I can measure the time. I still know the velocity initial is 0, but I don't want to know about velocity final now. Forget about that one. Now I want to figure out what the acceleration is. So I have to pick the equation down here that has these 4 variables. That's going to be this equation right here. We do not have velocity final in this equation, so we're going to select this equation right here. All right, so pause the video again. You are going to get acceleration by itself. Okay, since you've paused the video, I want to go ahead and give you guys a trick here. So we know that the initial velocity is 0 when something is falling, when something is being dropped. So we can actually, this whole section right here, we can just get rid of it because 0 times whatever it is still 0. So we're going to ignore that. And again, we want to get acceleration by itself because we're solving for acceleration. We've got these 3 variables and we're trying to figure this one out. We do not care about this one. Okay, so the first thing I'm going to do is multiply by 2 again to get rid of that. Then I am going to divide by t squared. And I do that because right here we've got multiplication. If I want to get rid of this, I have to divide. Now I'm left with acceleration. Acceleration equals 2d over t squared. All right, so I have my assistant with me today, Mr. Boykin, and Mr. Boykin is going to drop a golf ball from 4 meters up, and I'm going to time how long it takes from it to go from his hand until it hits the ground. Ready when you are.
Get set, go.
Okay, got it.
Let's do another one anyway.
Yeah, wait, we
We'll
were
write that number down.
So I got 0.57 seconds for my first one. Go ahead.
Ready? On your mark, get set, go.
Okay, I got 0.69 seconds for my second one.
Let's do one more.
Okay, I'm ready.
On your mark, get set, go.
Okay, I got 0.96 that time. All right, so using the data from when Mr. Boykin dropped the ball, I have 3 different times. Time 1, time 2, times 3. Okay, my first time was 0.57 seconds, 0.69 seconds, and 0.96 seconds. All right, so I've got 3 different times. I want to take an average of these 3 times to use in my equation. So how do I do this? I'm going to add them all up. Okay, 0.57 plus 0.69 plus 0.96, and I get 2.22 seconds, and I divide by 1, 2, 3. And I get my average time is going to be 0.74 seconds. This is the number that I'm going to use up here. So I'm going to go ahead and start plugging some stuff in here. So we'll start with the time at the bottom, so 0.74 seconds squared. Let's look at the top. So we know we have to multiply it by the distance or the displacement. And Mr. Boykin was 4 meters up. Now, my question for you guys is, what was the direction that the ball was going? And because it was falling, our direction or our displacement is going to be negative because displacement is a vector quantity. It has magnitude and direction. So we're going to say times 4 meters, but it's going to be a negative 4 meters.
And falling is a negative experience.
Yeah, yes. So we don't want to, Mr. Boykin knows that all too well. So I'm going to go ahead and plug this into my calculator. So 2 times -4 gives me -8. I'm going to divide that. Don't forget to square this. 0.74 seconds squared. And I get -14.6 meters over seconds squared. Now, before we go any further, let's talk about how the reliability of this number. The time that I got for each of Boykin's 3 trials were really different, right? 0.57 seconds here, almost 0.7, almost 1 second. So because these were so different, we have to keep in mind that this time that we got is not super reliable. So the answer that this should be is going to be a little bit off based on what we know this acceleration should
What
be.
should the number be, Ms. Moore?
I'm glad that you asked. So the number that it should be is right here. Near the surface of the Earth, all objects fall with an acceleration of -10 meters per second squared. On the AP tests, and from here on out in AP Physics, we are going to be using this number for acceleration. Last year, you guys might have used 9.8. This year, we're going to use 10 because we use the number so much, and you can use that on the AP test too, as well. So we're going to practice with -10 meters per second squared for acceleration. Now again, we got 14.6. So this number is not the same thing as that number, -10 meters per second squared. The question is, why is that? This number is too large. Why? Well, where did it come from? We measured a couple of things. We measured the distance, how high Mr. Boykin was up, and we measured the time. The time is the one thing that I was measuring by hand that wasn't exactly that reliable and consistent over here. So I think we need to take a look at this. My next question for you guys is, if you look at these two fractions, which fraction is bigger? Well, it's this one. And why is it bigger? It's bigger because the number on the bottom is smaller. So this answer is bigger than it should be. And the question is why? Well, the number on the bottom right here is smaller than it should be. So if we come back over here, you'll notice that as the trials went on, my number got a little bit bigger. This number right around here probably would have given me a number closer to -10 meters per second squared. Now, if I would have kept doing more and more trials, then I bet you this average time that we used probably would have been a little bit better. So near the surface of the Earth, all objects fall with this acceleration, -10 meters per second squared. And again, the negative, because we're falling and we're going, our displacement is down, our change in position. So this number, -10 meters per second squared, is a very special number. We call it the acceleration due to gravity, not just gravity, acceleration due to gravity, and it is represented by the letter G. And like I said, we're going to be using -10 meters per second squared for this number. And so for our kinematic equations, everywhere that we saw an A for acceleration, we can insert G for acceleration due to gravity when something is falling. So you see here, here, and here we have gravity inserted in. So anytime you have a question where something is being thrown or being dropped, you can use -10 meters per second squared as the acceleration due to gravity. This is sort of similar to how initial velocity, if it starts from rest, is 0 meters per second. It might not tell you explicitly in the question, but you need to know this. Okay, so now what I want you to do is give it some practice. Page 49 through 50, do these numbers. Rock and roll, baby.
And they don't have a book, so.
I'll figure out how to get that in there.